the major announcements have been from Microsoft and Google announcing Majorana 1 and the Google Willow quantum processors. Each of them have been unveiled in the last few months. They are using very different qubit technologies. They have a very different performance characteristics. They are doing very different architecture. They have a very different scalability and error correction between them. So when it comes to the technical comparison, I would compare it this way. So we have topological qubits in one case, then we have superconducting qubits in the other way. One is around encoding the topology, the other is more focusing on the extensive error correction. While using digital voltage pulses, the other is using microwave pulses. One is using special new materials, the other is using already established superconducting materials. If you are able to make a mark on the screen using the tooling, feel free to do that. The question is, how much do you think we are close to this quantum supremacy thing? I have been checking both companies' announcements and everything, so there has been a lot of marketing around it and everything, but there are a lot of technical things. So I'm just curious about those people who are on the call. Where would you consider? Are we close to this side or are we closer to this side? So are we nearly having the quantum supremacy or are we just even starting to get close to it? So feel free to make a mark if you can or you want. I will leave 2 minutes for us to. Is that a smiley face? Yeah, that's a smiley face.
I did my best.
No, you did amazing. You did amazing. So thank you for this whole drawings and everything. And we wouldn't be in a crazy, active, whatever world if something wouldn't have happened today. So today, out of a surprise, Amazon announced the new Ocelot chip, which is also a new quantum chip. So I actually didn't have Amazon on my bingo card for quantum for this month. So I was like, oh, okay. That was in some way unexpected. But without further ado, I would like to announce Moody's as our special guest, and I will stop the screen share because, as I mentioned, the rest of the thing would be an open discussion between us and about this topic. So I will start with the obvious question. Multiple of you put we are very far from the quantum supremacy, and some of you put we are pretty close to the supremacy. So I would like to hear both sides quickly if they would explain why they do think that we are either very far or very close to it. Sandra, you know you have to drop in a few minutes, so if you can share 2 words before you drop, that would be fun.
I think if you asked a physicist or a quantum scientist when quantum computing would be possible in the year 2000, they would probably have said by the end of the century. Or maybe even, oh, never. This is more a mathematical construct for us to have fun. A few years later, the first qubit was realized. And everyone was like, oh my God, we may have something. Be sure little algorithm is not just a mathematical construct after all. So if a few years later you ask the same scientist, he would say maybe in the 60s or 70s, perhaps, if we're lucky. Fast forward in the 2015 or something, we already had quite a handful of qubits. We had entanglement, mainly superconducting and trapped ions. People would say, yeah, maybe in the 50s, but this is still very far away. It's almost impossible to get these qubits in a proper coherent state so that we can do computations on them. I'm sure you all know, yeah, I'm going. The evolution has been exponential. If you use, really like to use evolution cues, measurement of, so the question they ask every year is, what do you think are the chances to have a cryptographically relevant quantum computer by 2030? If it is cryptographically relevant, most likely is going to be computationally relevant also to do things that are good. This is always the offensive and defensive element. And the percent of people that think that is going to be possible before 2030 has been growing steadily 1%, 2%, 3%. And I think this year is about 6% on the higher trends. The breakthroughs that we've seen since the end of last year in error correction on new qubits, on new ways of entangling the qubits, or new error mitigation and correction techniques has been so massive that now the industrialization of the qubits seems closer than ever. I'm still skeptical on how we're going to put all the elements together, the full value chain. But a lot of the blockers that people in the 2010s and 2015s were skeptical about are almost out of the way. So now it's just getting that stuff together. Microsoft announcement obviously has been big, but it has some asterisks there.
Yeah, it has a lot of usually. I think they had something that the marketing team was like, yeah, make it sound nicer. The same for Google Willow. That announcement is big, but what the marketing team did around it might have been a little overshoot. Same way.
It's the magic of quantum. You
Yeah.
say there's this Willow thing, and then what people get says Google uses the multiverse to make computations. Okay, fine. You did an experiment for a problem that has zero business value, but huge scientific value as a stepstone on what we're trying to build. Same goes for Microsoft. They have been working, many people thought they were fools. Uh, and
They went like 180-degree different than anyone else.
But the other day, they showed the world that they have been onto something. A lot of people, myself included to some extent, we were like, oh my God, they haven't done it, but they will do it.
Yeah, they are this close to actually find Majorana. So they are,
Exactly.
don't know whether this close is 1 year or 5 years. You know,
I would put them at the moment before they were not in a race.
Amazon wasn't in the race for me actually a few weeks ago, and now they are like announcing their chip.
Right. They built their compound a couple of years ago. They announced that we're working on this and they were working on superconducting technology, but they were silent because their goal was we're just going to move directly towards the device.
Yeah.
Similar to Quantum strategy that also released a really nice note yesterday or this morning in terms of scaling the wafers, the photonic wafers that they have been working on. You put all this together, and it seems that my biggest bet with some of my colleagues was in 2030 for computationally programmed computers, and I may be too far on when things may be a reality.
If we are looking at regulators, because we are in finance on the other side, so they are saying, oh, it's still like 2035 and things like this. Whenever I see them, those I'm like, I'm a little hesitant to believe it's going to be that long.
I think you're right. And the difference is whether something is used for defensive purposes or for offensive purposes. In finance, we are usually not the fastest technology adopters in the world unless we have a huge regulatory deadline. And then we would do whatever it takes to scramble. But then we would comply with that. However, when it comes to use a technology that can generate a massive competitive advantage or that can bring in the right stock price high or things like that. And if suddenly we get access to a little tool that can increase the performance of our funds,
If suddenly you can do portfolio analysis or any kind of thing suddenly faster, that's going to be faster, more precise. My big thing so far is everybody is completely is the wrong word. Everybody is concerned about the energy need of AI. What's going to be the energy need of quantum? Will it be comparable? More?
for most systems, the energy would be less. However, when you add the full stack and the error correction, with the systems that we have today, in order to scale to, say, a million qubits, you actually need, for some of these systems, a stacked skyscraper of data centers.
Yeah.
With the stuff that we have today, that we have today. So obviously we wouldn't do that. It's impossible. It's not feasible. To get 1,000 logical, all connected qubits, the amount of energy and servers and racks that you have to put together is not feasible to get the
You
whole.
can put them in the cloud.
But still, you need all that compute, all that power. Now,
No, I understand that, but it will be the cloud providers and not my problem.
I think with new types of error correcting modes, cat qubits, for example, that provide
Yeah.
different scaling laws, then the quantum humanity is actually much cheaper than what we need today in order to train the 10,000 H100s and train them now.
Yeah, no, so for me, the big breakthrough in my mind going to be when this whole thing will run on room temperature.
And so
Because the biggest energy is the cooling. We know that.
it,
Yeah, but there are some architectures that operate at room temperature, like trapped ions, but they have other problems.
Yeah. So I hope that these things will eventually meet together, like room temperature and the error correction. Everything will come. We have seen the same thing happening on so many other technologies. I'm looking at everything from smartwatches to self-driving cars and everything, where all these things came together eventually. And now I have a mobile phone which has the computational capacity of 20 years ago, super cray machines, something like level. And yeah, it's happening over and over. Yeah, but the big question is, if we are saying that the regulator's deadline of 2035 is wrong, what can we do today? Yeah, the obvious thing is start using post-quantum cryptography methods here and there and everything, which is, I find it always funny that when a company says, I'm doing quantum, and okay, what you do? I'm like, I'm doing post-quantum cryptography. Yeah, that's about avoiding quantum. You are doing everything to avoid using quantum in some way, which is very funny. Yes, we are trying to avoid the attack curve using quantum, so it's, but still funny in some way.
actually, the PQC part, we believe that must be either a cybersecurity enabler or a partnership between a quantum team and cybersecurity. But the way post-quantum cryptography works today, it is the job of the CISO to understand, hey, there's a new threat, same as site attacks or AI attacks and so on. It has this, it has these new algorithms, these new sign-in certificates, these new classical algorithms. So once you have monitored and evaluated and you get the NIST guidelines and so on, in my opinion, the CISO responsibility. What we do at Moody's is work together and evaluate those things. Quantum communication, that is a quantum responsibility. It may more, maybe probably more Horizon 3 and so on. But post quantum cryptography, sure, you need to understand what are you fighting against. And other than that, you're talking about crypto agility, inventory management, crown jewels management, and so on, which is something that is 0.1% quantum, 99.9% cybersecurity.
So when I'm going to have my Star Trek teleporter finally, that's something that many people still have a little problematic understanding. This whole, when they say we teleported a gate, we teleported a state and so on, that wording is very confusing.
It, it is. And when you start your path in quantum, uh, one of the very first circuits that you create, one of the first problems that you have to solve is the quantum teleportation algorithm.
Yeah.
It's a relatively simple, very simple algorithm. It is that you implement with a few quantum gates. So you implement that with Circ, Qiskit, any framework out there. And you think, oh, look, I have teleporting something. That's fantastic. Obviously, that is not true. You then learn about the no freelance theorem and stuff like that. And it is teleportation, but not quite to some extent. And
If you look at the Star Trek thing, they always say that it's not the matter that goes there, only the information, and they destroy the matter in the original place and rebuild your matrix, whatever, on the other side from stored materials in the. So if I look at it from that angle, then it might be the Star Trek teleportation, actually.
I think that so the problem is that even though the quantum state is teleported, you still need to send a piece of information over a classical line to understand how to measure that state,
Yeah.
to observe it. So there is no actual teleportation if you still rely on the speed of a classical system to say, use this observable or that observable. So again, it's a fake teleportation. So when people think, oh no, with quantum, this was was in the news a lot in the
Yes.
quantum computers will help you teleport. Uh,
I remember that. That was
they-
like, I'm like, what?
which when we think about exploration, for example, and how do you build a network that goes to Mars?
Yes.
And you want to, at some point, we will have some kind of base in Mars and we will want to communicate with people there. And of course, there is quite a bit of a delay, slightly longer than East Coast to the West Coast. So you would want to communicate with them. So people came and said, hey, this is the solution for moon bases and Mars based networking capabilities. So we have real time communication. People can watch Netflix and from Mars. Like, well, not quite, but it sounds like nice, like a quantum Netflix.
Huh.
Hold on, I need to write.
Yeah, it was we had to trademark this.
Yeah, but I do leave you in the hands of Carmen.
Yeah. Karan, continue this discussion. What is your opinion when we are going to have the quantum supremacy? We heard your boss's opinion. I'm curious about yours.
I think that these experiments demonstrate that all the main points that we needed to work on, we are not encountering any fundamental blockers. So I agree with Sergio in the sense that it's not anymore a matter of if, but a matter of when. Everything indicates that we have several proposals for architectures. We still don't know which one will win the race, which is also interesting. Each of the architectures, of the hardware architectures, have their pros and their cons. But what is clear is that the progress have been very, very fast paced in the last 50 years. And we looking at the roadmaps from the providers, we can only predict that it will eventually happen. Um, so I cannot predict exact date, but what I can predict is that it will happen, and therefore we need to prepare because there's a lot of work to do to understand where you can benefit from this technology. And you will not just it will not be a plug and play kind of
Oh, it's not.
work.
I don't know whether any of the other participants ever tried to write code. It's a very different way of writing code. There are cross compilers. I actually saw some interesting cross compilers trying to cross compile C code or C++ code into something that can run on a quantum simulator. It's not impossible technically, but yeah, it's a very different one. But yeah, this is an Ask Us Anything session, so feel free to unmute and ask questions from either of us on this topic. So we want to have a fun discussion among the people here.
What particular challenges does Microsoft still have left with their chip? What's the blockers?
Okay, yeah, that's a very good question. So the
Yeah.
first thing is that they have announced that they created the first topological qubit, but there are still some of the properties that a topological qubit should have that, at least in the paper that they published, are not evident. And again, keep in mind that they only have one qubit so far. So what can they do with one qubit? The good thing about this new kind of qubit, it's that it may have, if it's true that they created, it should have longer longer coherence times, which means you have more time for doing computation before the first error occurs. Longer coherence times enable better computation without errors, and therefore you need less error correction. Error correction techniques introduce an overhead because you need more physical qubits to create one logical qubit that has the nice properties and that where you can perform all your computations. Therefore, this is a desirable property for a qubit. But it's like they are right now at the time of having a chip that has, and therefore They are like when IBM, at the point like when IBM created their first chip. Now they need to demonstrate that this can scale up and that the properties that you expect from a qubit from a processor with multiple qubits also are maintained when you introduce more qubits. Because the real use cases that will give us the biggest advantages require on the order of millions of qubits. So therefore, we're still far from there.
As your point
Very
about
good answer.
scaling up then, is the issue then just with the manufacture, say, of the nanowires that have to be precisely laid down atom by atom in order to create a chip, and that's the bottleneck. Is that a bottleneck within the manufacturing process, that everything has to be so perfect?
I'm not an expert in hardware, but what I can say is that for most architectures, when you add more qubits, the interaction between the qubits also introduce errors. This is why you need to, in theory, you could build a chip based on superconducting qubits and manufacture 1,000 of them or how many as you want. But the problem is that every single qubit will interfere with the others. So this is what they need to try to avoid. But again, I could point to some resources, but I'm not
Yeah.
a hardware expert. I don't know if
So
maybe
yeah,
Peter, you have
so
more comments.
yes, the whole thing is about both the cooling and the size. The problem is right now the physical separation between the qubits, even in the Majorana chips, has to be relatively big. Being able to put, I don't know, 1,000,000 qubits, which would be really this quantum supremacy level and everything. How do we have to think in a football field size thing, or should we thinking something that fits in my hand? That's really the question. No one would be able to build something that's a football size field and can be kept cool and can be kept interference free long enough to make good calculations. So it has to be something smaller. That's where topological qubits should be a solution for making it smaller and less interfere with each other. But as Carmen mentioned, the actual paper that Microsoft published does not have all the evidences yet. I'm not saying it does not do it. I'm just saying the actual paper does not have all the evidences that they found the holy grail of quantum yet. They might. So same as with Sergio, I was a little skeptic. Actually, I was skeptic about many of these companies, but some of these announcements and some of these white papers tell me that the whole subroom, that this whole thing might be much closer than you would think.
Okay, thank you.
Sure. Anyone else, any questions? This is a topic your company might not be related with, but as Sergio and Carmen and I mentioned, you will. Either from the post-quantum cryptography side, which is, as we mentioned, is just was just another security hygiene. You had to deploy something for Heartbleed, you had to deploy something for this or that cipher, and also this is not going to be different from that perspective. It would be something that your security team will deal with. The other side, whether it's the quantum communication or quantum computation, is the new side of the thing that your company might not yet be willing to focus on, but eventually it will come. And as Sergio mentioned, and I have that feeling. So when I was around 2000, I was under the impression it won't happen in my lifetime. No, I know it will happen in my lifetime. I just don't know when, which is a huge change in the approach to this whole thing. And whether it will be applicable for everyday life, whether I will have a mobile phone having a QPU, a quantum chip, in my lifetime, not sure. But also at the same point, I'm not sure I want that or I need that. Same way as you are not using the GPU for everything or the MPU or everything in your life, in your development world and so on. Same way you will use these quantum processing units only for particle things. Same way as it's relatively expensive to move data in and out of a GPU, same way it's relatively expensive to have the quantum machine set up and you to read the results back. So you would make the decision based on the computation need on whether you want to run it that way or not. Okay, any other questions to us?
So is there a current agreed upon definition of quantum supremacy? So is it breaking a given algorithm? What is the definition that we talk about?
All right, you want to take this?
Yes, I think that's a very good question because some companies don't like that term, quantum supremacy. They would rather talk about quantum advantage. So, quantum advantage is defined as the moment when a quantum computer is able to efficiently solve a problem, a real world problem that no classical computer in the world could solve efficiently. But quantum supremacy does not require the problem to be a real world problem. And therefore, this created the debate on whether this was a useful measure, because if you can demonstrate that it does something better than classical computers, but it cannot be applied anywhere, what's the use of that?
Yeah, so when Google announced Willow, they made this claim that they can solve something in a few minutes that otherwise would take, I don't know, septillion years or what was the actual number. And people like, oh, this is amazing. And then you looked at what the problem was, and you were like, actually, that's not a, mm, not a realistic problem, or not. It doesn't make sense, the problem. But you could feel like the problem was set up in a way that their chip would be able to solve it faster than a classical computer. Sure, yeah. But did it bring any benefit? Not really.
Yeah, I would like just to add that the test that they used is a good benchmark to assess the progress of each generation of chips. So that's its purpose. But we need to work on problems that are relevant to our world. And this is quantum advantage. So this is the real goal.
I would like to thank everyone for joining us. As usual, please try to join all our mail groups and everything else that you can do. Let me just flash quickly or the information on that. So please do join our website, read about the stuff, and please do join the mail group if you haven't done so. Probably you have already joined it. And otherwise, I would like to thank everyone for joining and wishing you an amazing day. And thanks for Carmen and Sergio for joining us.